So it's probably most frequent problem where you need to calculate the density of a function of random variable. So the problem is that you have a y which is equal to the sum of x1 plus x2 plus so on plus xn. And it can be just sum of independent measurements, for example, in examples. So it arises when you look at the something like a sample mean. So if you have several measurements and you calculate the sample mean of these measurements, then you'll have something which is called x bar, which is equal to 1 divided by n, x1 plus xn, where these are kind of just measurements of a random quantity. Well, so in statistics, it's a way to estimate expectation of this random quantity. So if you have many measurements, then you can believe that the average of them is kind of a good approximation of what's expected value, kind of the expected value of this quantity. And so, and to calculate distribution of this x bar, to say something about say something about quantiles of this distribution, you'll need to know how to calculate the distribution of a sum. So in our example, that you might have a something like a u is equal to x plus y, and say x, it's it's a random quantity, but it's measured something like a signal, signal, something which you are interested in, and y is something which is not very interested, so it's a noise. And so you kind of want to figure out how the distribution of the this quantity observed signal, how this distribution depends on the distribution of a signal and distribution of a noise. Often you will have a converse, inverse problem from distribution of observed signal is find out what's the distribution of a signal, find out what's the signal, but it's one component in this problem is to figure out what's the a direct problem, how to calculate the distribution of observed signal from the distribution of a signal and distribution of norms. So this is a right. So one 6 for hope. Right. Okay. Um, so need to feel kind of half what and distribution many how figure out distribution of so now so let's do it using a PDF. All right. Okay. So so here's okay. So um, here's how we do it. So we have a u is equal to x plus y, and we want to apply the PDF um, PDF transformation method. So we'll need an additional random variable, so additional function of these two random variables, because we want to have a one-to-one map. So the idea is to define another variable, which is v, kind of, right? So, and we can choose any function of x plus y such that we could go back from u and v to x and y. So we can choose x, or we can choose y. So any simple function. So let us choose y. So kind of let us choose y. So the plan is before we calculate the joint density of E. So that's the first thing. So joint density of U and V. And second thing, so kind of after we calculated this joint density, so we will be able to calculate the marginal density. Okay, so right, so now this is easy to do in this case because we can do the inverse transformation is easy, right? So y is just equal to u, right? And x kind of from these equations we will see that x is equal to u minus y, but what? So y is equal to v. Right? Y is equal to v from the second equation, so from this equation. And x is equal to u minus y. So u minus y. So y is equal to v, so u minus v. So this is our inverse transfer. Additional thing that we will need is that we also So this is tough kind of today. Additional thing that we'll need a Jacobian, right? So Jacobian of this transformation. Right? So now the functions is u minus v and v. So Jacobian is just equal to, right? So it's determinant. And after that, we write the matrix of the partial derivatives. Right? So we'll need to take the derivative of this function, u minus v, with respect to u. This will give you 1. And also the derivative of this function with respect to v. This gives you minus 1 in the first row. Then you look at the second row. This here is the function v, and you again take the derivative with respect to u, u 0. And the derivative with respect to v, which gives you 1. And also kind of, when the definition Jacobian is usually multiplied by 1, so 1 times 1, so it's equal absolute value of 1 times 1 minus 0 times minus 1. Okay, so it's equal to 1. So kind of a Jacobian is very easy here. It's equal to 1, so we can ignore the Jacobian. And then after that, we just write, okay, so what's the joint density of u and v at points u and v? And so it's just equal to the joint density of x and y evaluated at x and y, which corresponds to this u and v. So, well, kind of, and to figure out what's the points that correspond, here's our inverse transformation. So x is equal to u minus v, and y is equal to v. And in principle, we need to multiply by Jacobian, but here Jacobian is equal to 1. So kind of this is it. This is a joint density. So this is a joint density of u and v if you know the joint density of x and y. Now, so we are not interested actually in the joint density of u and v. We are interested in the just marginal density of u, just in the density of u. So we kind of can write that f of u. And then now kind of we just write a general kind of formula that it's equal to integral from minus infinity to infinity of this f of xy. And here you have a u minus v dv. So you integrate all kind of this from this thing. And so alternatively, you can kind of do a change of variable and write it slightly differently, maybe in a slightly more usual form, traditional form. So it's equal to integral from minus infinity to infinity f of xy. And if you call this stuff t, so then it will be here t, and the second v kind of, well, t is equal to u minus v. So v is equal to, so if you have t is equal to u minus v, then v from this equation is equal to u minus t. So here will be u minus t. So integrated over dt, because this is kind of right? It seems to be that there is some kind of university problem, kind of with a connection. Right, so hopefully it is resolved. Okay, so so here's what we got, right? So this is our formula, right? So for the marginal density, so for the density of the sum, u is x plus y here. So here is x plus y is a density, but we can simplify it. And so we can simplify it if we know that the x and y are independent, right? So if x and y are independent, then so what we got in this case, that we have that f of x, y, so the joint density of these two things, it's a product, right? So it's f of x, f of y. So it's just by definition of independence. And if you plug in the previous formula, in this formula star, and so then the formula becomes a little bit, well, kind of different. So we'll have a f of u, it's equal to the integral from minus infinity to infinity. And here just kind of, well, kind of in this formula, the formula star, I plug in this expression for the density. And I'll get that this is equal to f of x, so density of x, evaluated at not at x but at t, right? So plugging in the arguments in the formula star. So multiply by f of y of u minus t, right? N over dt. Right? So this is a formula star. And so now this is kind of this is the formula. You can apply this formula and get the kind of a density of the y. So one thing here is so first of all it has a name. So this is called a convolution of functions f of x and f of y. And so kind of, well, kind of it's not only defined not only for the density function, but in general kind of. So you can write it for any function f of one variable and y of other variable. So just kind of, so here's t and u minus t, sum of them is equal to u. And so kind of it's easier to write down this formula. And so it's a convolution of functions fx and fy. And we can apply this formula. So in this formula, I kind of, so it's a little bit kind of, well, slightly misleading in the sense that it's very easy to write here. But in principle, if you want to write down formula, kind of, and find out what's the integral in the specific cases, then you will need to talk about ranges and so on. So now this will be a little bit more difficult kind of to apply. Right? So so this is kind of maybe worthwhile to say. And so in general formula, kind of you write the integral from minus infinity to infinity. If you want to calculate this formula analytically, then you'll need to take care about the ranges. So that kind of, because this f of x of t, it's somewhere it's equal to 0. In other places is equal to some analytical formula. Maybe in other places some other analytical formula. So, well, it becomes cumbersome if you do it analytically, kind of just want to figure out what's the formulas. And but theoretically, it's this is kind of very easy kind of formula. And so now also it turns out that, well, kind of you think about numerically, it's also you don't care about the ranges. Right? So in the numerical case, if you want to do calculation numerically, then this f of x of t is just given some procedure. Computer gives you computes it by using some procedure. Right? And if you calculate this integral also by approximating it with some Riemann sum. So in this form also numerically this is approximated with Riemann sums. And so kind of, which means that you evaluate this function at some specific grid of points of t, and after that, instead of integral, use the summation. So I just want to correct a kind of impression that you might have from the previous lectures that this is somehow very difficult kind of thing. So it's not so difficult if you do things numerically. Kind of, it's difficult to derive analytical formulas, but numerically, kind of all the formulas are typically very easy. Kind of, so kind of calculating the joint distribution, it just involves kind of calculating the Jacobian and inverse function. Right? And calculating the marginal usually it involves just calculation the integral, which is also easy to do numerically. And so, well, it's numerically it's easy thing. And so maybe kind of will give us let's look at the example. Although kind of, well, this may be a little bit more kind of, well, examples we are doing not numerically, but kind of analytically, so it might be a little bit cumbersome. So example, so let's look for an example when x and y are uniform on the interval from 0 to 1. And in this case, kind of, we'll need to calculate u is equal to x plus y, and we want to calculate what's the u is equal to x plus y. Right? And we want to calculate the density of u using this formula, this convolution formula. And so now, so we know that f of x is equal to 1 if x belongs to 0 and 1, and 0 otherwise. And similar for f of y, right? So because it's kind of, well, it's uniform, right? So now we want to calculate this f of u using this formula. And so we're using this formula, integral from minus infinity to infinity of f of x of t, f of u minus t dt. Right? And so first of all, kind of we can immediately notice in this case that, well, kind of f of x of t, it's equal to 0 if t is outside 0 and 1. So in principle, we can write it a little bit simpler. So here's y. So we can write that this is equal to the integral from 0 to 1. And so, and on 0 to 1, f of x of t is equal to 1. And so it's equal to integral from 0 to 1 of f of y u minus t dt. And so kind of, well, and after that, well, unfortunately, this thing depends on you. And so if you, so this is the formula. So we'll need to just look at the different maybe cases for this thing. So so again, so maybe kind of to understand what we need, well, first of all, we look at u, which is equal to x plus y. So the density should be on the between 0 and 2. Kind of the random variable u cannot be smaller than 0 and cannot be larger than 2. So we are, at least we assume that u is greater than 0. And so now here is the t, and here this will be f of y u minus t. And so now this f of y u minus t, it's equal to always equal to 1, right? But it's kind of depends on where it's equal to 1. So u minus t is equal to 1 if, sorry, f of y of u minus t is equal to 1 if u minus t it belongs to the interval from 0 to 1. Right? So it's by definition the last thing. So now we are looking at kind of when, so we are looking at the graph of this function when it depends on t. So we'll need just to write that this is equal to, it's to interval from 0 to 1, so which we can write that this is u minus t smaller than 1, smaller than equal 1, and greater than equal than 0 if t is smaller than equal than u. Okay? So this is from this inequality. So t should be smaller than equal than u, and it should be from the second inequality, t should be greater than equal than u minus 1. U minus 1. Right? And it's equal to 0 otherwise. Right? So now kind of, okay, so what I'm doing here is I'm trying to calculate this integral, but for this I need to figure out what's this function, right? How it looks like. Okay, so I take the integral from 0 to 1, but kind of I need to know what's kind of the function, right? So that thing says that it's between, it's equal to 1 between u minus 1 and u. And so now first thing to look at kind of when u is between 0 and 1. So let us look at the case when u belongs to greater than 0 and smaller than 1. Smaller than 1. It's the first case. So now the interval here will be this like that. So this will be u. Here will be u minus 1. Okay, so now a function will be equal to 1 on this interval. Okay, so this is, I just draw a graph of this function, how it depends on t. Okay, so given that this parameter u is between 0 and 1. Okay, so now this is this picture, right? And then I'm integrating from 0 to 1. So it's equal kind of when I'm integrating from 0 to 1, I'll get that this is the integral equal to the area under the curve. So it's equal to this area, right? So this area, well, kind of it's equal to 1. This function is equal to 1. This area is equal to u, right? So, right? So from this I got that this integral. So this integral here is equal, so if the f u of u equal to this integral, it's equal to u if this condition satisfied. So if u greater than equal than 0, smaller than equal than 1. And in this case, it's u. Now, if in this case, this density is equal to 1. If u was smaller than 0, then, well, kind of this interval would be, this interval from u minus 1 to u would be outside. It will be smaller than interval 0 and 1. So the integral would be equal to 0. And so now, okay, so we know that u, the range of this random variable u is between 0 and 1. So we'll need to kind of between 0 and 2. So here we'll look at one case when it's between 0 and 1. There is another case between when u small is between 1 and 2. And so let's look at the picture in this case. So this was the first case, and second case it is when u is greater than equal than 1 and smaller than equal than 2. And so again, so we'll need to draw a similar picture. And so it will be like that. So here is a t, and here we want to figure out what's this f of y of u minus t as a function of t. Right? So here's 1, and here's so here's 0, 1, and now we are saying, okay, that u is between 1 and 2, right? So this is our u, right? And this interval u minus 1 u, so this interval where this function is equal to 1, it looks like this. This is u, and here's u minus 1. Okay, so, and at this interval, our function is equal to 1. Okay, so this function f of y of u minus t is equal to 1. Right? But I'm integrating from 0 to 1, so I'll need to figure out what's this distance. Okay, so now, not this distance, what's this area? So what's this integral of this function from 0 to 1? Right? So to apply this formula, so it's equal to area, so it's a height is equal to 1 multiplied by the base, right? And base here is equal to 1 minus u minus 1, right? So it's equal to 2 minus u, right? So it's equal to 2 minus u if, so this is just kind of 1 minus u minus 1, if u is greater than equal than 1 and smaller than equal than 2. Right? Well, and if it's u becomes greater than 2, then you can see that this interval here, right? So this interval here, so it's sliding, right? So if u becomes greater than 2, then this interval becomes non-intersecting with the interval from 0 to 1. So kind of, so this is interval over which we're integrating. So now the range of u becomes not intersecting with, not range of u, range of this function becomes, well, maybe range of this function becomes non-intersecting with the interval of integration. So the integral will be equal to 0. To summarize what we're just saying, kind of, it's everything is equal to 0 if if u doesn't belong to the interval from 0 to 2. So otherwise, so this is the answer, right? So, well, kind of, you can see that kind of, well, we can plot this density, right? So just to see how it looks like. So this is f of u, so which we found, and it's equal to kind of, it's non-zero and for interval from 0 to 2, and it's equal to u kind of here on this interval, it's equal to 2 minus u here. So this is our density which we found. And so you can see that this is kind of cumbersome because you need to consider some particular cases, but, well, kind of, it's just kind of calculation of this integral. If you would did it numerically, then, well, you just kind of plug in these functions and kind of say integrate, and kind of the computer numerically integrates it, well, kind of just by doing some kind of a summation, approximating with some kind of a summation. So in this case, you would kind of just look at this formula. So program this formula and just say kind of integrate. And we would need to know kind of how to calculate all these particular cases. So, okay, so, but this is illustration how this method works, this PDF methods works in this specific example. And so calculating the sums of the two random variables, and you can generalize it to many random variables. The integral, well, kind of, well, the integral will become more complicated in this case, but you can write it down. Right, so, okay, so let's make a small break now, and next time we will see how these calculations can be done by using the MGF method. All right, maybe let's restart. So now, okay, so method of MGF. And so moment generating functions. So now just to recall the moment generating functions. So so MGF of Y. So well, I'm not sure why I call random variable Y. So say X is okay. So it's AMX of T. So T is just some parameter. And so and it's equal to the expectation of E Tx. So this is a function of a random variable. So this is expectation of E of T of X. Well, and it's called moment generation because it's, if you write it down as a Taylor series, then you will get something like this: 1 plus first moment M1 of X. And so first moment of this random variable X multiplied by T plus second moment, so maybe M2, I call it without writing T, of T squared divided by 2 plus third moment, M3 T cubed divided by 3 factorial, and this K is equal to expectation of X to the power of K, and so it's a moments. So this is a moment generating function, and why it's called a moment generating function, because, well, if you differentiate this function enough time and evaluate it at t equal to 0, then you'll get the moment. And so now, so the main idea of this method is actually moment generating function. It's unique for any random variable. If you have a distribution of random variable, some specific distribution, you call it MGF, you'll get some function. This is function just for this specific distribution, for now nowhere else. So if you know MGF, then essentially you know the distribution of this random variable. So now the method of MGF is based on the fact that you can easily calculate the MGF of the sum. So so we have a theorem, right? So which says that under some condition, if S is equal to x1 plus so on plus xn, and so this is important, and x1 x2 xn are independent, then you can write down the MGF of the sum. So MFS of t is equal just to product of the MGFs. M of x1 of t multiplied by M of x of t, sorry, mx2 of t multiplied by so on, multiplied by M of x 3, so xn of t. And so now this is it's important thing here is that the random variables are independent. And so this is one restricting condition. And the second thing, well, you can calculate easily the MGF of the sum of the random variables. Right? So, but the problem is that, well, even if you know the MGF of S, it's not necessarily means that you can easily calculate the density function. So the difficulty is that it is not easy to get from MGF to PDF. So if you know the MGF function, it's not easy to calculate what's the probability density function of this random variable. There is a function, there is a a method, there is an integral, but it's okay. So it's just, you will write down you will write down the density as an integral, and after that the only thing that you can do is go to the numerical software and use this integral kind of to calculate the density. And so if you're really interested in the analytical functions, then it's better that you recognize this MGF, that it's MGF of something which you already know. And so can be done numerically. It can be done numerically, and it's usual in mathematics. In mathematics, that so numerically it's okay, but you need some analytical formulas. And in mathematics, it turns out that there are some specific examples in which you can do it, and which is because of this are very important. So all other examples just kind of becomes like approximation of this thing. So in some specific example, some specific examples, you can recognize this MGF as MGF of a known distribution. So, well, kind of, and this is what we are talking about now in this chapter, about kind of some specific example when it is possible to do in this section, right? So in this lecture. And so for example, if you go back to the example about the sum of two uniform distributions, right? So kind of, well, you can kind of calculate the MGF for uniform distribution. You can calculate the kind of product of the two of them. It will be square of them. But it's you cannot recognize it as a kind of distribution of this density, kind of this which we got before, right? So you cannot recognize it as the MGF of this density, because this is not familiar density. So what you can do is you can invert the MGF of the sum of these two random variables and get this density. But kind of if you resolve to the numerical integration, then this formula is equally good, kind of, right? It's not, there is no advantage into going to the MGF method. So MGF method is nice because it allows you to do some specific examples in which it can be done without doing the integration. Right? And so this is not the example, right? So uniform, if sum of the two uniform distribution, MGF method doesn't give you any advantage in this example. So now what are the examples? It turns out we already looked at most of them. So here's an examples. So this is example one, and this is probably the most kind of important example, which is a sum of the normally distributed random variables. Okay, so this is number one kind of importance for this thing. So x1, x2, xn, and nice thing about this one, we can do it for many random variables, right? So in the PDF method, it would be very difficult to write down the multidimensional integral and to calculate the density of the sum. And so here we assume that x1, x2, xn are normal random variables with means. Okay, so mu1, mu2, mu_n, and variances sigma1 squared, sigma2 squared, so on, sigma n squared, okay, respectively. So kind of x1 have a mean mu1 and variance sigma1 squared. x2 we have mean mu2 and variance sigma 2 squared. Okay, so all right. So now the right. So let us apply this method to this example. Right. So we want to figure out what's the distribution of S, which is equal to x1 plus so on plus xn. And then if you want to apply MGF, we need to recollect what's the MGF of a normal random variable with a given parameter. It turns out that in this case, so with m of xi of t, well, kind of going back to what I did before, actually I didn't even calculate it, but said that it is possible to calculate. It's equal to e to the power of mu I t plus sigma I squared t divided by 2. T squared here, sorry. So mu I t, so this is kind of the first thing, and sigma I squared divided by 2 t squared. And so now, all right, so after that it's very easy, kind of, so write that m of s of t is just equal to the product of this thing. So it's m of x1 of t multiplied by f of xn of t, right? And if you would take the product of these things, right? So it's a product of exponential functions, so it's exponential of the sum. Yeah, so you'll see that this is equal. So let me write here exponential, right? So kind of right. So not. So it will be equal to exponential. Okay. So and after that we kind of rearrange things and we'll have it exponential of mu1 plus mu, sorry, plus so on plus mu n. Okay, so here we'll need to remove it. So plus mu n t, plus after that we'll have a sigma I square plus, so sigma 1 square plus sigma 2 square plus so on plus sigma n squared. And here's t squared divided by 2. So we'll look at this and recognize that this is MGF of a normal distribution. Right? So we know MGF of a normal random variable with the parameters which is given by this parameter and this parameter. So it's a MGF of a normal random variable with mean mu equal to mu1 plus so on plus mu n, and variance sigma squared, which is just equal to sigma 1 squared plus so on plus sigma n squared. So the important fact not that it's the mean of the variance of this random variable. Important thing that it's normal, kind of, right? So it's a form of a normal distribution, right? So we can conclude that the sum of the normal random variables, of independent normal random variables, I need to say here maybe it's a very important here, independent. I missed here random variables. And so the conclusion, so this is essentially a theorem, and conclusion is that S is normal random variable with mean mu and variance sigma squared. It's a normal random variable, right? So with this mean and variance. Mean and variance can be calculated for the sum and for the sum easily, kind of, even if it's kind of not normal, right? But this is a normal random variable. And so, well, kind of, you can ask the question, what happens if they are not independent? In this case, it's nice thing about the normal random variables that if it's jointly normal, then the sum will still be normal, kind of. But we are not kind of talking about this here. It just kind of can be proved, but it's in this case, it's you need to get to look at the probability density method, kind of to do it, or kind of do more sophisticated method. And so in this case, we'll kind of just sum of independent normal random variables, and this is the conclusion. And so this is kind of probably the most important application of this method. And so there are kind of a bunch of other examples, right? So we look at many of them before. So example two. So suppose x1, x2, xn are exponential random variables with parameter beta. And so here it's not so interesting because it's in the previous example we had mu1 and mu I and sigma I, they can be different for different random variables. Here it's important that this parameter is the same for all of them. And so it's also kind of always independent. Okay. Okay, so independent. So exponential and parameter beta. So in this case, kind of, so if you apply this method, then you'll get what's the MGF of this xi. Right? And so it turns out again, so I will not do this calculation. So we calculated before, it's easy to calculate that it's equal to 1 minus beta t. And so that's it. And so 1 minus beta t. And so now, well, okay, so so if you define s is equal to x1 plus so on plus xn, okay, so then in this case you'll find out that m of s of t, okay, that's equal, okay, so it's product of the moment generating function for each individual random variable. So it's equal to 1 minus beta t multiplied by itself n times, so it's to the power of n. And so we look at this and say, all right, so at least this is not exponential because it's not 1 minus beta t, it's something different. And so it's not exponential, so sum of exponential random variables is not exponential. Right? But well, kind of after that, we can look at the list of all MGF and hope that we will find some MGF which is kind of corresponds to this specific MGF. And then if you look attentively, then you find out that there is an MGF which is kind of looks like that. So it turns out that this is a MGF of a gamma distributed random variable. Okay, so now with, well, specific parameters, in this case gamma, it depends on two parameters. One of them is alpha, and this parameter alpha should be set to n. Right here it's n. And beta, well, beta is equal to beta. Right? So parameter beta will be the same as here. Right? So now kind of, okay, so we know that the initial distribution. So, well, I mean distribution by initial distribution, I mean distribution of xi, distribution. So distribution of xi is, so it's e minus x divided by beta. So again, so initial distribution, maybe not initial distribution, so maybe kind of density. Sorry about this. Density of xi is e minus x divided by beta, and here's 1 divided by beta. Okay, so, and it looks like this thing. Okay, so the distribution of x1 plus so on plus xn. Again, so by distribution I mean density is right. So this is something very kind of, well, kind of some constant here. And after that it will be x to the power of n minus 1. Here's e minus x divided by beta. And here's will be 1 divided by gamma of n. So it's okay, n minus 1 factorial. And here's beta to the power of n. Yeah, beta to the power of n. Right. So now, so this was an original distribution f of xi of x, and the kind of the distribution which you'll get here is just looks something like that. Right. So this is f of s of x. And so, but kind of, well, just this is just one specific example. And kind of, if you think about this, is pretty well kind of miraculous in the sense that it's not so easy to calculate it really kind of by doing the convolutions of these random variables. And so you can try to kind of do the convolution, and there will be some integrals, and it turns out that these integrals will give you eventually this formula. Right? So that the sum of the exponential, so you will start with this distribution and convolve it with itself n times, then you'll get this kind of a distribution. Right? So this is the second example. So so it is possible to generalize kind of this. So, but I will skip it. Maybe kind of just tell you. So kind of, so just kind of state it kind of, right. So example 3. It's more or less clear how to do it. So x1, x2, xn are gamma distributed random variables with parameters alpha 1, alpha 2, so alpha n, right? And beta, same for all xi. So this is these are shape parameters, and this is scale parameter, and scale parameter is the same for all of them. Then kind of x1 plus x2 plus so on plus xn is gamma distributed with parameters alpha is equal to the sum alpha 1 plus alpha 2 plus so on plus alpha n and beta. And it's clear how you do it, kind of, you know the MGF of every of them. It's 1 divided, so kind of the MGF of every one of them will be something like that. Right? So if instead of n, you will have alpha. Right? Alpha 1, alpha 2. After that, you multiply it. Everything will multiply. We'll get 1 divided 1 minus beta t to the power of sum of these alphas. Right? And so this is, you can identify it as the MGF of a gamma distributed random variable with the parameters alpha 1 plus so on plus alpha n and beta. Right? So kind of, it's kind of more or less easy generalization. And another maybe example slightly different, right? And it's different in the sense that, well, kind of here we talk about the densities always. So this was example, I guess, 3, and this is 4. It's slightly different. So here we talked about continuous random variables always. So, but MGF method, it actually works for discrete random variables as well. And so in this case, you will need to think about it. You're calculating not the density of the sum, but probability mass function of the sum. And so, but just you calculating the distribution of the sum of the random variables. So here's an important example about the discrete random variables. So they're important because they are very kind of rare, kind of not so many examples in which you can really identify the MGF of the sum. And so, and that's why they're kind of rare, and because of this, they're important. Rare cases when you can really write down a formula. Right, so now, so here's x1, x2, xn, Poisson random variables with parameters. Okay, so for every one it's parameter lambda1, lambda2, so on lambda n. So these are means of this random variables. So these random variables are kind of Poisson random variables. You can kind of mnemonic is that it's about some accidents, right? So kind of it's, and lambda1, parameter lambda is average number of accidents per kind of unit of it's average number of accidents, at mean number of accidents, right? So kind of a PDF of this is kind of a PDF was equal to P of xi, so maybe just of x, say, of x of say k, right? So the probability that x is equal to k is equal to e minus lambda, lambda to the power of k divided by k factorial. Okay, so this is kind of a definition of a Poisson random variable. So this is a probability mass function, PMF. So, and we'll need also kind of to know what's the MGF of this thing. So, and again, so kind of it's not easy to remember, but you can look at the kind of table and see that MGF of this M of x, M x of t, it's equal to E, and here's lambda ET, well, kind of, I'm not sure, kind of, I'll need to check actually if it's right or not. Kind of, I'll forget about it, I forgot about this. Yeah, this is right, yeah. AT minus 1. So, right, so kind of now, this is for general kind of thing. So now what we want to do is to kind of to take a product of these MGFs, right, for each individual random variable. So if S is equal to x1 plus x2 plus so on plus xn, then MGF of S, M of S of t is equal to the product of MGFs of this thing. So it's equal to E lambda 1 ET minus 1 multiplied by E lambda 2 ET minus 1, so on, multiplied by E lambda n ET minus 1. Okay, so now you see that this is equal to E to the power of lambda 1 plus so on plus lambda n ET minus 1. Well, kind of, and this is MGF, so it's MGF of a Poisson random variable with mean lambda equal to lambda 1 plus so on plus lambda n. And so kind of, okay, so you know that S, so that S is this, so S is a Poisson random variable with mean, so with this mean lambda, right? So Okay, so, and well, if you think about this again, so kind of this is a kind of very surprising. If you think about how you would do it without knowing this method. So, and again, so everywhere where I say I forgot to write that these are independent. They should be independent, otherwise it doesn't work. So if you think about how you would do it differently without knowing the MGF method, then kind of seems to be difficult. Kind of. Right? So, except maybe kind of using the intuition, intuitively it's clear that kind of summing the number of accidents, if they are independent on in different places, then it should be a number of accidents overall. So kind of, right, so, okay, intuitively it's clear, but how to prove it, it's you will need some method, and this is the only method that you can do in this case. All right, so now, the bad thing about this thing is that you cannot apply it in different situations. Right? So these are the situations, practically listed almost all of these situations when you can do this stuff. In all other situations where recall is either to PDF method and doing it numerically, or kind of you can also say that you can use the fact that if you calculate MGF, you might not be able to figure out that it is MGF of something known random variable. But you can find out that maybe it is close to the MGF of a known random variable. That the kind of that this function MGF is differs only by a small amount, especially maybe in some region kind of. So it's closely approximates something. Right. In this case, you might kind of argue that it is the PDF of the sum is also closely approximates the PDF of this known random variable. And this is what is done in the proofs of several theorems. Otherwise, well, kind of, it might be useful to do it numerically if you know MGF, and you can always do inverse transformation, but it's not big advantage maybe on the well, kind of, this is kind of, you'll need to figure out whether it's advantageous with respect to the just numerical calculation by using the density transformation method. Right, so this is a moment generating method, so we will cover it today, and so this is the covers the triple of these methods. So it covers the cumulative distribution method, which is sometimes useful because of its simplicity, the probability density transformation method, which is kind of the main method, kind of, right? Something like, well, kind of usually kind of applied in most situations. And moment generating method, which is useful to get some analytical formulas in some specific examples. And so it's important because of this ability to get analytical formulas, explicit formulas. So next time, so this is all for today. Next time, what we are going to do is to look at the order statistics. So, and this is a specific case of a function. So one important case is sum of the random variables. In other important cases is kind of, if you look at maximum or minimum, this is also natural things. And order statistics is just generalization of this maximum and minimum functions of several random variables. Right, so this is what we are going to do next time. Okay, so so that's all for today. Sorry for these interruptions. It's kind of seems to be university-wide problem. And if you have questions, stay. If no questions, then that's it for today. Have a nice weekend. Do we need to remember the CDF method? It seems like the PDF transformation method works better every time. And what kind of a situation with CDF method work, but PDF method don't work? Well, you know, you ask a good question, but so I don't really know when kind of a CDF method is more useful than the density method? Well, in our second example, you know, when we had the x and y, and we looked at the different x minus y, I think that the effort was actually comparable for the cumulative distribution method and the PDF transformation method. So because these are really complicated examples, and in this case, even PDF method, if you need to get a formula, then in this case, cumulative distribution method might be as good as the probability density method, maybe even easier. So